Breaking news from the farthest reaches of our solar system. 3i Atlas is no longer acting like the comet astronomers thought it was. Just days ago, telescopes recorded something extraordinary. As this mysterious wanderer closed in within 2 astronomical units of the Sun, its behavior shifted dramatically. Instead of following predictable models, its brightness began skyrocketing. Even more shocking, its coma or atmosphere expanded until it stretched out to nearly half the size of the Sun itself. Its glow took on a strange, almost haunting green color. And in the most puzzling twist yet, it formed a tail that points back toward the Sun, something that by all known laws of physics should be impossible. Now, as it speeds toward Mars at astonishing velocity, scientists are being forced to admit the truth. They cannot explain what is happening. The countdown to its closest passage by the Sun has begun, and every hour this cosmic stranger looks less like a comet and more like a riddle demanding answers. Stay with us until the end of tonight's deep dive, because what you're about to discover could change everything we thought we understood about the universe, and reveal what happens when alien chemistry finally stirs awake. This is part 1, and the simple fact is this: 3i Atlas isn't just getting brighter, it's expanding in ways that challenge explanation. The data does not lie, even when it breaks every rule. In mid-September of 2025, astronomers monitoring the object noticed their predictions starting to unravel. Instead of holding steady around magnitude 15 or 16, its brightness shot into the range of 12 to 14. For anyone unfamiliar with the strange logic of astronomical magnitudes, here's what that means. The lower the number, the brighter the object. Just 2 steps down can mean a 6-fold increase in brightness, and this wasn't unfolding gradually, it was accelerating at a shocking pace. The global tracking network known as the Comet Observation Database, or COBS, recorded this runaway curve as data points began climbing above every expected model. Ground-based telescopes confirmed the same startling trend. 3i Atlas was now outshining every forecast astronomers had proposed for its approach to the Sun. The turning point came as it crossed inside 2 astronomical units, about 186 million miles from the Sun. For comparison, Earth sits just 1 astronomical unit away, or roughly 93 million miles. Even at twice our distance, something fundamental within Atlas seemed to awaken. The acceleration in brightness was not only unusual, it was alarming. What could cause such an eruption of light? One explanation points to exotic ices buried deep in its core. We're talking frozen water, carbon dioxide, and potentially far stranger materials that condensed when this object first formed somewhere around another star. Under the Sun's growing heat, those frozen compounds don't simply melt, they vaporize explosively. They leap directly from solid to gas, blowing away dust and debris, building enormous clouds and throwing sunlight back toward Earth as they expand. But there's a catch. Rapid brightening like this almost always means instability. When comets release too much gas and dust too quickly, they often rip themselves apart, splitting into fragments or unraveling into spectacular clouds of rubble. Others simply burn themselves out, their reserves depleted in a sudden burst, leaving them to dim almost as quickly as they flared up. The terrifying part is that Atlas is behaving outside every prediction. That means we may be watching something astronomers don't fully understand unfolding right before our eyes. Thankfully, there's no danger to Earth. NASA has confirmed that Atlas won't come closer than 1.8 astronomical units from us. That's still nearly double the distance of Earth from the Sun, and far too distant to be a collision risk. The real alarm isn't about safety, it's about comprehension. We may be witnessing an interstellar relic undergoing dramatic changes for the very first time, as it plunges toward the heart of our solar system. Think about what that means. This object didn't form here. It was born in the swirling debris cloud of another star, perhaps hundreds of light years away. It's made of materials that have never once felt sunlight, never shaped by the same conditions that molded comets and asteroids in our neighborhood. For billions of years it drifted untouched in the frozen dark of deep space. And now, for the first time in its existence, it's experiencing the full intensity of solar radiation. What we're seeing could be the sudden awakening of alien chemistry that hasn't stirred since the dawn of its creation. These rare ices, stable only in the frigid emptiness of interstellar space, might be sublimating now for the very first time. In other words, Atlas could be revealing chemical fingerprints from another star system perfectly preserved until this moment. The clock is ticking. Atlas is heading into a series of crucial encounters that will determine just how much we learn from it. On October 3rd, it makes its closest pass to Mars just 30 million kilometers from the red planet. That proximity means spacecraft already orbiting Mars might record details invisible to us on Earth. But the real test comes at the end of the month. Between October 29th and 30th, the comet will swing through perihelion, its closest pass to the Sun, at around 1.36 to 1.4 astronomical units. Here's the problem. For observers on Earth, that is exactly when Atlas begins to vanish into the blinding glare of the Sun. From early October through early November, its position places it in what astronomers call superior conjunction. That means our best view of its peak behavior, the instant when solar radiation is at its hottest and its chemistry most violent, will be hidden from Earth's skies. We'll have no choice but to rely on the robotic eyes of spacecraft positioned deeper in the solar system. In particular, those orbiting Mars may end up capturing what could be the show of the century, an interstellar comet erupting with unheard-of activity as it faces the Sun's fury head-on. And if current data is any indication, Atlas will not go quietly. The acceleration in brightness suggests it's building toward dramatic outbursts, explosions of gas, light, and dust that could peel back the layers of its structure and reveal clues about its alien nature. But will these explosive secrets emerge while Earth itself is blinded by sunlight, unable to watch? The September data shows one thing clearly. Atlas is changing before our eyes. Its light curve is no longer following any predicted path. This visitor from another star is transforming into something entirely new, rewriting expectation with every passing night of observation. The big question now is whether what we're seeing from 3i Atlas is just an extreme version of normal comet behavior, or if it represents something entirely new, something we've never encountered from an interstellar visitor. Over the next few minutes, we're going to break down exactly why its atmosphere, or coma, is stretching farther than physics says it should, why its tail is bizarrely oriented toward the Sun instead of away from it, and what its sudden shift into a ghostly green glow could mean for alien chemistry. The mysteries here are piling up as quickly as the numbers climb, but first we need to step back and understand what this object really is. Because Atlas isn't just another comet, it's the third confirmed interstellar visitor in all of recorded history. And if the last two taught us anything, it's that these wanderers don't play by our rules. The journey of 3i Atlas began on a mountain ridge high in Chile, where robotic telescopes sweep the sky each night with precision no human eye could ever match. On July 1st, 2025, one of those robotic sentinels, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, spotted a faint blur shifting against the fixed background stars. At first, it was logged as just another small body, one among countless minor objects that pass through the database every week. But that quiet little discovery didn't stay unremarkable for long. Within weeks, it would be recognized as one of the most extraordinary finds of the century. What qualifies an object as interstellar isn't simply that it came from beyond our solar system. It's the fact that its trajectory makes return impossible. Unlike comets from the Oort cloud, which are slowly pulled back by our sun's gravity, Atlas is racing on a hyperbolic path. That means once it swings by the sun, it won't loop back, it will shoot back into interstellar space forever at escape velocity. The mathematics of orbital mechanics confirm there's simply too much energy in its motion for gravity to ever reel it back. Its very name encodes that story. The Roman numeral I stands for interstellar, and the 3 indicates it's only the third such visitor humanity has ever documented. The 2 that came before, 1i Solar Miyamura in 2017 and 2i/Borisov in 2019, already shattered expectations. Chava Miyamura was a bizarre cigar-shaped object that accelerated in ways no comet or asteroid had before. Borisov looked more like a traditional comet, but carried chemicals alien to our solar system. Now Atlas takes the 3rd chapter of this ongoing story, and its behavior is proving just as strange, if not stranger. Catching something like this is no small feat. The Atlas survey, which detected it, operates through the Rio Hurtado Observatory in Chile's Atacama Desert as part of a planet-wide program designed to spot potential threats long before they get near Earth. The system snaps repeated images of the same patch of sky, then runs software to spot anything moving against the static star field. That night in July, 3i Atlas was nothing more than the faintest of smudges, a streak that blended almost seamlessly among the thousands of asteroids and chunks of debris orbiting in our solar system. But digging through older images revealed the truth. Atlas had been hiding in plain sight in archived data weeks before its official discovery. That lag is common with interstellar objects. At first, they often look deceptively asteroidal, just another rocky speck before suddenly growing the coma and tail that reveal comet-like behavior, and Atlas wasted no time. Even in those early frames, astronomers noticed the faint beginnings of a surrounding cloud, clear evidence of sublimation, the process where solar energy causes its deep frozen ices to vaporize and stream into space. What shocked astronomers was how early this activity began. When Atlas was first spotted, it was still over 3 astronomical units away, more than 270 million miles from the Sun. At such a distance, sunlight is weak, and typical comets stay silent and frozen. But Atlas was already shedding mass, already cloaked in a spreading coma, proof that its nucleus contained highly volatile compounds that vaporize even under faint solar heating. That revelation made astronomers sit up and take notice. Soon bigger instruments were aimed at this alien traveler. The Hubble Space Telescope provided crisp imagery in July, while Chile's Very Large Telescope and others around the globe added their measurements. These detailed follow-ups showed that the little faint blur was anything but simple. Atlas was already a challenge to pin down. Its solid core remained hidden beneath the hazy glare of its coma, making size estimates tricky. In August, Hubble's best calculations suggested a nucleus somewhere between 0.3 and 5.6 kilometers across, small compared to planets but enormous compared to man-made spacecraft. This wide range reflects how difficult it is to measure the actual solid body when it's buried under a glowing shroud of gas and dust. The size matters for good reason. It directly influences how much mass the object carries and whether it can survive repeated outbursts as it nears the Sun. But while questions remain about its body, one thing became clear very quickly: its speed. Atlas is tearing through space at around 58 kilometers per second, about 130,000 miles per hour. For comparison, Earth orbits the Sun at a relatively leisurely 30 kilometers per second, less than half that speed. And as Atlas falls deeper into the Sun's gravity well, those velocities will only intensify. At perihelion, it could be hurtling past at 68 kilometers per second, more than 150,000 miles per hour. Numbers like that are unheard of for native solar system comets. Only something forged in another star system and flung into the void by alien gravitational encounters could carry that much velocity across interstellar space. That speed is the smoking gun of its origin. A visitor shaped, not by our Sun, but by countless interactions across the galaxy. Each gravitational nudge, each stellar encounter fed momentum into its path until millions of years later, it arrived here by chance. That's what makes every confirmed interstellar object a priceless find. Before 2017, no one had ever directly observed such a body. We only theorized about how they might look or behave. Then Oumuamua arrived and broke all the models with its strange form and unexplainable acceleration. Borisov followed with icy chemistry never before seen. Now Atlas adds a third piece to the puzzle, another unique case that forces us to rethink assumptions. Already its massive coma and runaway brightness leave scientists struggling to explain what they're seeing. And this is only the beginning of its story. Every interstellar visitor we've seen seems to follow its own strange set of rules, as if each one carries a unique blueprint of how planets and comets form in its home system. What this tells us is that the galaxy is far more diverse in its small world chemistry and physics than anyone ever imagined. Classifying something like 3i Atlas isn't as easy as stamping it with a comet label. Astronomers need to figure out whether it looks more like an asteroid, behaves like a comet, or is something so strange it might redefine categories altogether. The fuzzy shroud we've detected around it strongly suggests comet-like behavior, but the real answers will come from spectroscopic data. By analyzing the gases and dust released, astronomers can begin to uncover exactly how Atlas formed and what exotic ingredients it carries from its parent star system, which could be millions or billions of years in the past. This isn't a local comet kicked out of the Oort cloud. This is something far stranger. 3I Atlas condensed in an alien system under temperatures, pressures, and chemical conditions different from anything in our solar neighborhood. That makes it a direct sample of planet and comet formation from literally light years away, a frozen time capsule that's only now waking up under the blast of sunlight. The orbital path this object follows is giving humanity a unique test case. Its trajectory will put it dangerously close to Mars on October 3rd, providing spacecraft orbiting the red planet a front-row seat to details invisible from Earth. And that timing is no accident. Just as Earthbound telescopes lose sight of it in the sun's glare, spacecraft beyond Earth will have their clearest view, handing us a precious observing window. But if you want to understand why this encounter is so important, you have to look not just at where it came from, but at what it's doing right here and right now, under our sun's radiation for the very first time. Its current behavior is something even the best astrophysical models didn't see coming. Time is running against the astronomers trying to decode this object before it vanishes into solar glare. The math of orbital mechanics leaves little mystery about its path. It's on a carefully charted course, and the key dates are locked in. The first crucial milestone comes on October 3rd, 2025, when it passes just 30 million kilometers from Mars. To put that in perspective, that's about 0.2 astronomical units, and unusually close in cosmic terms. This means a host of orbiting spacecraft, NASA's MAVEN, the European Trace Gas Orbiter, Mars Reconnaissance Orbiter, and more will have the ability to record this alien traveler in stunning detail. But here's the frustrating irony. While Mars-based spacecraft may enjoy their best viewing window, astronomers back on Earth will be forced to watch opportunities slip away. Because at nearly the exact same time, Atlas's orbit carries it directly toward the sun's position in our skies. That angle creates what astronomers call observational geometry challenges. Simply put, Earth-based telescopes will soon be blinded by sunlight. The most critical date will arrive later in the month. Between October 29th and 30th, Atlas will reach perihelion, its closest point to the sun. At this moment, it will sit about 1.36 to 1.4 astronomical units from the solar furnace, just inside the orbital radius of Mars. Here it will endure solar heating, unlike anything it has ever faced during its long interstellar drift, and yet that's exactly the moment when observing it from Earth will be nearly impossible. Its speed only adds to the drama. Right now Atlas is racing through space at tens of kilometers per second, but at perihelion, it could hit jaw-dropping velocities close to 68 kilometers every second, or about 152,000 miles an hour. Imagine this: Earth itself orbits the sun at around 30 kilometers per second. Atlas will be moving more than twice that speed, carrying the unstoppable energy of millions of years spent crossing the gravitational landscapes of other stars and the Milky Way's rotation. The path puts Atlas close to the ecliptic plane, the flat disk where most planets orbit, naturally setting up its brush with Mars this year, and in 2026, a distant pass near Jupiter. Statistically, it's sheer luck that an interstellar nomad from random three-dimensional space would align this well with planetary orbits. Yet here it is, offering multiple chances for observation. And for anyone still worried about what if it hits Earth, astronomers have already ruled that out completely. The object won't come closer than 1.8 astronomical units to our planet, almost twice Earth's distance from the Sun. NASA has confirmed there's no collision risk. For scientists, the only danger here is missing the chance to study something this rare. The real problem is timing. From early October through early November, Atlas will be caught in what astronomers call superior conjunction, a period where its position hugs the sun's glare so tightly that even the best telescopes on Earth struggle to separate the two. Solar elongation, the angle separating the comet from the sun in our sky, will drop below 30 degrees, and that means trying to see Atlas from Earth is like trying to spot the twinkle of a firefly hovering next to a stadium floodlight. Even deep space observatories can't overcome that problem when it's in Earth's line of sight. And that's the cruel irony: at the exact time the comet is expected to reach maximum activity, outgassing at full force, maybe splitting apart or growing spectacular tails, Earth's astronomical community will effectively be watching blind. Any fireworks might happen behind the sun's glare. That's when orbiting spacecraft step in. Missions around Mars like ESA's Mars Express, NASA's MAVEN, and others suddenly become essential, not just as Mars scouts, but as humanity's only active eyes during this critical window. The data they collect may be all we get until the comet swings into a safer observing zone. What happens after perihelion is anyone's guess. If Atlas survives its trial by fire intact, it should reappear in Earth's skies by late November or early December when the geometry improves. But by then much of its energy may be spent. After exhausting its volatile reserves during the solar encounter, it could fade quickly before observers get much of a second look. At its brightest, it's expected to peak near magnitude 11 or 12, faint enough to require telescopes and far beyond naked eye visibility. For casual sky watchers hoping for a spectacular display, Atlas might disappoint. But for scientists, the real treasure lies in the chemical fingerprints and dynamic behavior playing out, because this is not just another comet. This is a messenger from another star system, and every second of observed data could answer questions astronomers have been waiting decades to ask. Once Atlas makes its closest pass by the Sun, gravity immediately begins to act as a brake, slowing the comet as it starts its journey outward again. This shift in speed directly affects how long it remains at maximum heating and how much observing time Mars-based spacecraft will have. Looking farther ahead, trajectory models show that after leaving perihelion behind, 3I Atlas will continue outward, eventually swinging near Jupiter in March 2026. While that flyby will be much less dramatic than the Mars encounter, it may still provide valuable opportunities for robotic missions to record data before the comet leaves our solar system for good. This creates a rare and extremely limited window. Unlike the repeat appearances of periodic comets, interstellar wanderers like Atlas pass through once and then vanish forever. If we fail to collect key observations during this brief stay, the chance will never come again. With conjunction, solar glare, and timing stacked against us, scientists are racing the clock. The real question isn't only what 3I Atlas will reveal, it's whether we're equipped to catch the revelations before they disappear. Orbital mechanics set the schedule, and no human timeline can change it. And with that, we arrive at the most staggering discovery about this comet, not its interstellar origin, not even its velocity, but the sheer size of the atmosphere it is generating around itself. In September 2025, NASA's SPAR-X telescope detected a carbon dioxide coma so immense that it shattered scientific expectations. Stretching over 348,000 kilometers from the nucleus, this eerie halo is nearly half the diameter of the Sun. For perspective, its atmosphere is large enough to swallow Mercury's entire orbit. Nothing like this has ever been recorded in the history of comet science. To call it unusual isn't enough. It's unheard of. A coma forms whenever solar heat strikes the ice locked inside a comet's nucleus, forcing it to vaporize directly into gas without melting. The classic dirty snowball, in sunlight analogy, only scratches the surface. In reality, the process is violent. Explosive jets of gas erupt from beneath the surface, dragging dust and rock along with them, and swelling into a glowing atmosphere that can swell to planetary scales. In Atlas's case, however, this isn't the ordinary mixture of frozen water and dust. Spectroscopic data reveals that carbon dioxide dominates its composition, vastly outweighing the usual presence of water vapor seen in comets from our solar system. That detail alone tells us volumes about its origins. To have so much frozen CO, Atlas must have formed in the far reaches of another star's protoplanetary disk, where temperatures were so low carbon dioxide could freeze solid while water mostly remained gaseous. No comet born in our solar system experiences that exact recipe of temperature, chemistry, and pressure. This is a direct fingerprint of alien formation conditions. And yet, chemical composition isn't the only oddity. Images from Hubble and Earthbound telescopes show Atlas forming not the classic tail sweeping away from the Sun, but an unsettling feature called an anti-tail, material visibly pointing sunward. This has left researchers baffled. For centuries, every comet ever observed followed the same principle. Sunlight and solar winds blow dust and gas away, forming tails always aligned opposite the Sun. Yet Atlas appears to break that fundamental rule. ejecting matter in the very direction it shouldn't. Hubble's July 21st observations showed what scientists dubbed a forward glow, a fan-shaped plume stretching sunward. By late August, Chile's Gemini South detected the same bizarre geometry persisting. This wasn't a passing quirk, it was stable and it was real. The usual explanations can't keep up. While large dust grains might theoretically resist being pushed by light pressure, needing enough mass and velocity to continue sunward, the sharpness and longevity of this feature make it unlikely to be just projection effects. Something about Atlas's structure or spin is pushing physics to the limit. One potential clue comes from its rotation. If the comet is spinning slowly, it might maintain extreme temperature differences between its day and night sides, directing gas jets in strange focused ways. Another possibility is that the chemicals on its surface respond to sunlight far differently than anything we've studied here, releasing energies and movements we've never accounted for in our comet models. The coma itself adds even more questions. Spectroscopic readings suggest Atlas's gases are escaping faster than in normal comets at the same solar distance. The explanation may lie in compounds so volatile they remained stable only in the deep freeze of interstellar space, now vaporizing explosively under even modest sunlight. Infrared observations also detected excess heat in the coma, implying additional reactions are taking place, perhaps energy stored in exotic ice crystal formations or chemical processes set off by mixtures never before seen in our system. And the coma isn't symmetrical either. Reconstructed 3D views from multi-wavelength observations show asymmetry jets and fans of gas, blasting out from specific sections of the nucleus instead of emerging evenly in all directions. This suggests Atlas's crust contains hotspots, localized patches of volatile rich material that erupt under heating. Such uneven activity gives astronomers direct clues to how Atlas formed, how its surface evolved through eons of interstellar travel, and what differences truly set alien chemistry apart from solar system chemistry. The dust thrown into the coma is another puzzle. Unlike comets we know, which tend to release fine grains, Atlas appears rich in unusually large particles. These massive dust grains provide one of the only plausible explanations for its enduring antitail. It's possible this body formed with a very different ratio of dust to ice, or that its long journey through the galaxy altered its materials in ways we still don't understand. And one final twist. Measurements show the coma doesn't just expand consistently, it surges and dips, its intensity fluctuating in patterns that may link directly to the comet's rotation. Each pulse of activity acts like a heartbeat, a rhythm of alien chemistry responding to its first encounter with sunlight. As Atlas pushes closer toward perihelion, its enormous atmosphere keeps expanding, swelling into something even grander as the sun's heat intensifies. But predicting what comes next has proven nearly impossible. Traditional comet models break down under the weight of Atlas's bizarre behavior. Its unusual composition, the strange geometry of its antitail, and the rapid outpouring of gas all require tweaks to comet physics that astronomers have never before attempted. In essence, researchers are being forced to rewrite their own playbook in real time, crafting new theories as the data continues to defy expectations. And that's the bigger picture. If interstellar comets regularly display such strangeness, then our entire understanding of cometary science might reflect only a limited corner of what's actually possible. What we've learned studying local comets may be just one small slice of a much broader spectrum of behaviors scattered across the galaxy. Each new interstellar arrival threatens to upend another piece of our carefully built models. For now, Atlas serves as the clearest reminder our science is a work in progress. The coming weeks, its flyby near Mars and its brutal encounter with the Sun will test these new models to their limit. But there's another piece of the comet's evolution that may be even more striking than its coma. In mid-September, Atlas turned green. This sudden transformation electrified astronomers. Practically overnight, the comet shifted from a pale object against the stars into something that glowed with a vivid emerald radiance, as though alive with energy. To the unaided human eye, the change wasn't visible. Atlas is still too faint, but cameras on telescopes around the globe couldn't miss it. Images showed an unmistakable green glow enveloping the comet's head. The effect became especially dramatic during the lunar eclipse on September 14th, when darker skies made the eerie hue even clearer, a haunting beacon in the shadowed night. This glow isn't just for show, it's a signal written in the physics of molecules. Here's how it works. When certain compounds absorb ultraviolet light from the sun, their electrons leap to higher energy states. When those electrons fall back down, they release photons of a very specific color. In the case of Atlas, the culprit seems to be diatomic carbon, two carbon atoms locked together, known as cathar. Under solar UV light, these molecules behave almost like cosmic neon signs, fluorescing at wavelengths around 516 nanometers. The wavelength corresponds precisely to the green light we see, turning invisible solar energy into a glowing emerald halo stretching across space. But here's the part that's confusing. Scientists' earlier spectral analysis of Atlas revealed very little carbon chemistry. Initial readings suggested a composition dominated by carbon dioxide, ice, and water vapor. Hardly the kind of chemistry that would produce such a vivid green display. So why the sudden burst of carbon-based fluorescence? The most likely answer points to hidden reservoirs of volatile compounds buried deep within the nucleus. When the comet crossed the 2 AU mark in early September, solar heat may have finally reached these hidden pockets, releasing carbon-rich gases for the first time in billions of years. The timing lines up almost perfectly with the rapid brightening surge seen in mid-September, hinting that both events came from the same explosive release of trapped material. Of course, that isn't the only theory. It's possible more complex chemistry is at play. Comets can contain dozens of carbon-bearing compounds, some of which are rarely found or not found at all in comets native to our solar system. The green may not come from a single molecule like cathars, but from a cocktail of exotic chemistry unique to interstellar conditions. And since each telescope uses different filters and methods to translate raw data into visible images, subtle differences in processing could shift the exact tint, sometimes making it appear emerald green, other times more turquoise or yellow tinged. That uncertainty adds yet another variable to the mix. What's clear is that the green light isn't evenly spread. Observations show pockets of intensified coloration within different parts of the coma, almost as if the glow is patchy and alive, flickering across the atmosphere instead of glowing like a steady bulb. This hints at uneven outgassing from the nucleus, with certain vents releasing carbon-rich materials while others do not. Alternatively, it could mean sunlight is actively breaking down complex organic molecules into fragments that release green light in bursts, painting the coma with irregular patterns of illumination. This color change isn't just visually stunning, it's a powerful diagnostic tool. The brightness and spread of the glow depend on factors like molecule density, gas temperature, and the strength of solar ultraviolet radiation. By studying how the green emission fades with distance from the nucleus and changes over time, scientists can actually map the three-dimensional distribution of carbon-bearing gases inside the comet's huge atmosphere. Early results suggest that these molecules are in thermal balance with the rest of the coma, hinting at efficient energy transfer as particles collide and interact. That detail gives researchers a glimpse into the inner physics of a comet unlike any they've ever studied. The sudden emerald shift of Atlas now joins Oumuamua's strange acceleration and Borisov's alien molecular chemistry as another crown jewel in the growing list of interstellar oddities. But unlike its predecessors, Atlas is glowing, quite literally, like nothing else before. Comet Borisov, the second interstellar object humanity ever observed, looked far more ordinary, its color palette dominated by soft blues and the white scatter of reflected sunlight. In contrast, 3I Atlas has become the very first interstellar comet to display that classic emerald aura more typically seen in local comets as they near the sun. But here's the catch. Its glow isn't identical. The intensity and precise wavelengths of Atlas's green hue might differ slightly from the ones we know, suggesting its chemistry is unlike any comet that formed in our neighborhood. It may be carrying exotic molecules forged only in the cold depths of another star system. The timing of this transformation adds urgency. The eerie green glow appeared in mid-September, just as Earth-based telescopes were starting to lose sight of Atlas to the sun's glare. And as October begins, the situation grows dire. When the comet reaches superior conjunction, moving too close to the sun's blinding disk, its evolution will unfold virtually unseen. For comets, the peak of fluorescent emission usually happens near perihelion, under the sheer intensity of maximum solar heating. That will be the comet's most explosive and chemically revealing stage. And yet, thanks to solar geometry, most of it might take place hidden from Earth. Spectroscopic studies have already begun trying to pin down the exact molecules behind the green glow, but these require massive telescopes, long exposure times, and stable observing conditions. As Atlas sinks closer to the Sun, those conditions become harder and harder to achieve. Every clear night left before conjunction has become precious, as astronomers scramble to collect what data they can. But make no mistake, this isn't just a pretty color shift, it's a physical transformation. That green luminescence tells us alien chemistry is stirring after eons of silence. The molecules fluorescing now have been locked in frozen darkness for millions, maybe billions of years, as the comet drifted in void between the stars. Now, under solar fire for the very first time, those long-dormant compounds are lighting up. The glow is a direct visual signal. Alien chemistry is awakening. And yet, what should be the most scientifically valuable period of this comet's life is also when it slips out of reach for Earth-bound instruments. This brings us to part 6, the challenge of observation. There's a kind of cosmic cruelty at play here. Just as this interstellar visitor reveals its most astonishing secrets, the runaway brightening, the record-breaking coma, the emerald glow, the geometry of its orbit conspires against us. No matter how advanced our telescopes are, you can't see what's drowned in the blazing glare of the sun. Even the most capable observatories face absolute limits. On August 6th, the James Webb Space Telescope managed to safely capture spectroscopic readings of Atlas with its near-infrared spectrograph. Those results gave us some of the most detailed chemical fingerprints of any interstellar object so far. But that was before mid-September, before Atlas lit up and shed every expectation. Hubble 2 delivered breathtaking images earlier in July, capturing the disturbing sunward plume we now call an anti-tail. Since then, though, the opportunities for high-resolution data have grown thinner and thinner, blocked by the sun's approach. Instruments like Webb and Hubble are designed with strict protective systems. They cannot even point too close to the sun without risking serious damage. As Atlas approaches conjunction, those systems all shut down. Ground-based observatories are no better off. Different instruments, different locations, and even the calibration methods themselves introduce inconsistencies in brightness readings. That's not unusual in astronomy. Measuring how bright something is requires precise adjustments for the atmosphere and for equipment variations. Still, across all those independent reports, one trend has stood out through September. Atlas keeps climbing above prediction. Its magnitude is brighter than every reliable model, even though the exact figures vary. Amateur astronomers, armed with backyard telescopes, continue to play a surprisingly critical role here. Their contributions fill the observational gaps professional teams can't always cover, but their results too come with added noise, local light pollution, weaker optics, and atmospheric distortions. Put together, however, the global community has been painting a consistent picture. Atlas is brighter, wilder, and more unpredictable than any comet we've charted before. The way solar elongation shrinks is the ultimate killer of these observations. That's the angle between the Sun and Atlas as seen from Earth. Once that drops below 30 degrees, even world-class instruments start to stumble, cross the 20-degree mark, and professional observatories typically give up entirely. By mid-October, Atlas will reach exactly that point, leaving Earth's astronomers effectively blind during the comet's most volatile weeks. Think of it like trying to watch a glowing firefly. Hover right beside a stadium floodlight. You simply can't separate the faint object from the overwhelming blaze. Even adaptive optics and coronagraphs, tools designed to tame starlight, are useless here against full solar glare. And so, once again, we're forced to rely on spacecraft scattered across the solar system. Machines like Mars Reconnaissance Orbiter, MAVEN, and ESA's Mars Express to act as humanity's surrogate eyes. They could be the only ones capable of witnessing Atlas during its climactic transformation, while Earth can do nothing but wait until the comet re-emerges weeks later. The very safety systems designed to protect billion-dollar space telescopes are now turning into barriers, cutting off our view of Atlas at exactly the wrong time. As conjunction approaches, instruments like JWST and Hubble will be forced offline just when the comet is expected to reveal its greatest secrets. Models predict that late October, the period around perihelion, could bring Atlas's most violent transformations, peak outgassing, possible fragmentation, and tales of unprecedented scale. These are precisely the phenomena that could expose its true composition and internal structure, yet most of it will unfold hidden behind the sun's glare, beyond human reach. And the obstacles don't stop there. Processing the images we do manage to capture is growing more difficult by the day. Astronomers must painstakingly strip away noise from starlight, cosmic rays, and instrument artifacts to isolate Atlas's signal. As the comet dims against the brightening sky near the sun, this task becomes even harder and prone to error. Spectroscopy, the gold standard for chemical analysis, demands much more than simple brightness readings. It requires dark skies, bright targets, and precision exposures, but as Atlas nears conjunction, all three are stripped away. The fainter it gets relative to the sun, the harder it becomes to split its light into wavelengths that reveal its chemistry. Ultraviolet emissions, the very signatures crucial for detecting exotic molecules inside comets, pose an even bigger hurdle. Earth's atmosphere scatters blue and UV light far more than red, which is why our sky looks blue. But that scattering blinds astronomers to UV signals coming from the comet at small elongation angles, exactly when those molecular fingerprints could peak. In short, the most valuable data is exactly the kind we'll struggle the most to record. That's why coordination among observatories around the globe has become critical. Telescopes in different latitudes and time zones are trying to stitch together every last piece of usable data. Southern Hemisphere sites may buy a little more time because of slightly better geometry, but even they are racing the clock. Every clear night counts. Every exposure is irreplaceable. Atlas is not coming back. Unlike periodic comets that offer second chances every few decades, this interstellar traveler offers one opportunity. Miss it, and it's gone forever. The scatter in reported brightness is another constant frustration. It's not just measurement errors. Sometimes the chaos reflects the comet itself. Outbursts, rotating vents, unstable structures, these can cause real changes in brightness on short time scales. The problem is, separating genuine variability from instrument scatter becomes nearly impossible with low signal-to-noise data. Weather makes it worse. Clouds, turbulence, and seasonal patterns at key observatories can wipe out entire blocks of planned observing runs. Every lost night narrows a window we will never reopen. Even interpreting the data we have is a challenge. Atlas's sudden leap in brightness in September may represent enhanced outgassing, a structural rupture, or simply flaws in our models. Sorting between these possibilities requires the kind of continuous long-term monitoring we no longer have as Atlas vanishes into sunlight. That responsibility now falls to spacecraft scattered through the solar system. Mars orbiters, probes, and robotic watchers built for completely different missions, suddenly acting as humanity's only eyes on this invisible drama. And so we enter Part 7, the growing alarm among astronomers. Behind the cautiously worded press releases and carefully qualified papers, there's a mounting sense of unease. Atlas is not following the rules, and scientists are beginning to admit that what they're seeing might be completely unprecedented. The data coming in from multiple sources is consistent. This comet is dramatically brighter than models predict. These deviations can't be explained away as statistical noise or instrument bias. From the Comet Observation Database to amateur networks worldwide, the same alarming trend is clear. Atlas is running hotter, brighter, and wilder than theory allows. Its light curve sits several magnitudes above expectation. That's not a subtle departure. That's a red flag. Dr. Matthew Knight, a comet specialist with years studying these enigmatic worlds, put it bluntly. The rapid brightening seen in mid-September doesn't fit standard models of comet heating. Comets normally evolve as slow, gradual processes governed by predictable volatile release. Atlas is breaking those timelines completely. The acceleration suggests something else entirely. Physical processes unfolding on far faster scales than any model assumes. For many scientists, this is unsettling but thrilling. The recognition that they are witnessing phenomena never before documented carries the promise and the burden of rewriting theory to match reality. Even popular astronomy outlets are reflecting the tension, updating the public with strange new behavior, while acknowledging nobody truly understands what's happening. The bizarre anti-tail structure adds to the puzzle. While not unheard of, Atlas's plume is far too persistent, too defined, and too sunward to be written off as a fluke of perspective. Researchers are now seriously entertaining exotic scenarios, non-standard dust grains, strange nucleus rotations, or surface compositions none of our textbooks cover. One fact isn't disputed. Atlas is more active than almost any comet at a similar solar distance. The coma, dominated by carbon dioxide instead of water vapor, stretches hundreds of thousands of kilometers farther than anticipated. The outgassing levels are staggering, far beyond baseline predictions. This doesn't look like a comet merely off by a few degrees. This looks like a comet rewriting the rules in real time. But astronomers are also wary of a trap they call outburst bias. Many comets can flare suddenly, reaching insane levels of activity before calming down just as quickly. Could September's spectacle be a temporary burst, giving the illusion of something extraordinary when it's just a dramatic hiccup? Or is this the rule-breaking heart of an interstellar object finally exposing itself? The fact that perihelion, when activity will peak, is mostly hidden behind the sun makes this uncertainty even more painful. If Atlas undergoes catastrophic fragmentation, chemical surges, or spectacular transformations, those moments may be lost forever. That possibility weighs heavily on researchers, as Dr. Carrie Holt of the European Southern Observatory remarked. It feels like a cosmic conspiracy against science, depriving us of answers at the exact moment questions multiply. And still the debates continue. Atlas's unusual chemistry, the inverted CO-to-water ratio, its alien coma composition, the glowing green emission, could mean it formed in conditions totally different from anything near our sun. Or it could mean its chemistry has been reshaped over millions of years drifting between stars. Either way, Earth's astronomers may only get fragmentary pieces of the story. In the meantime, the global astronomy community is mobilizing. Amateur astronomers fill in gaps, professional networks attempt to reconcile scattered readings, and international agencies like ESA track Atlas with every tool available. The broad consensus: this comet is brighter than it should be, stranger than expected, and racing toward a chapter that could permanently alter our understanding of interstellar objects. Even within the scientific community itself, the tone is shifting. On social platforms, in conference abstracts, in early papers, it's clear researchers know they're watching something significant. They just don't yet know what it means. Even the jade-green brilliance of Atlas adds another twist to the narrative, because its timing and intensity don't perfectly line up with its earlier measured chemistry. That mismatch teases the possibility of processes far more complex than our models can easily explain. And so, as October looms, Atlas carries with it the weight of mystery and anticipation. For astronomers, the comet has become not just an interstellar visitor, but a puzzle, a threat to established theories, and perhaps the most important cosmic messenger humanity has yet intercepted. The urgency among scientists is about more than curiosity. It's about recognizing just how rare this chance truly is. In all of human history, we've only confirmed 3 interstellar visitors. Each one provides a once-in-a-lifetime glimpse into conditions that shaped planetary systems light years away. Miss this opportunity, and the secrets vanish forever into the void. That's why collaboration has gone global. Observatories in Chile, Hawaii, the Canary Islands, and Australia are working in unison, trading data across time zones, and maximizing every remaining night of visibility as Atlas drifts closer to the sun and into solar glare. High-resolution images, specialized spectrographs, and sensitive cameras are being pushed to their limits to squeeze out every last observation before Earth loses sight completely. But there's another challenge: how to communicate this unfolding mystery to the public. Media headlines can sometimes overstate certainty, portraying speculation as fact or amplifying phenomena. Scientists themselves admit they don't fully understand. Researchers find themselves walking a tightrope, feeding public excitement over this unprecedented encounter, while remaining honest about how much is still uncertain. And then there's the unsettling side note. Atlas isn't dangerous to Earth. It won't come anywhere near our planet. But its unpredictable evolution highlights how little we really know about how these icy bodies behave when exposed to solar fire. If our models can't even predict Atlas with confidence, what does that mean for risk assessment when future comets on potentially hazardous paths are identified? Yet, this mix of alarm and exhilaration is what science is all about. Nature doesn't follow scripts. It consistently produces surprises that push us to expand our understanding. That's what makes Atlas so valuable. As October looms, Earth's view may dim, but spacecraft scattered across the solar system could be positioned to catch revelations Earth-based telescopes can no longer reach. And now comes perhaps the most exciting part, Part 8, the Mars flyby. While Earth prepares to go blind, Mars will step into the spotlight, offering a front-row seat to history. On October 3rd, 2025, Atlas will pass by Mars at a distance of just 30 million kilometers, about 0.2 astronomical units. For Mars, that's incredibly close. And orbiting the red planet right now are some of humanity's most advanced spacecraft, each with eyes sharp enough to catch details invisible from Earth. This is a golden opportunity. Just days before Atlas sinks into conjunction, Mars orbiters may deliver the best and possibly only detailed look at an interstellar visitor during its active transformation. The European Space Agency's veteran Mars Express, still running strong more than 2 decades after launch, carries the high-resolution stereo camera, a system designed to map Martian landscapes. It might now be repurposed to image Atlas's inner coma, and maybe, just maybe, resolve its nucleus. Meanwhile, the Trace Gas Orbiter, built to sniff out methane and other atmospheric gases on Mars, could turn its instruments toward Atlas's coma, searching for alien chemistry hidden in its expanding shroud. NASA's Mars Reconnaissance Orbiter brings perhaps the most tantalizing capability. Its high-rise camera can capture details smaller than a meter on the Martian surface. Though Atlas will still be distant, HiRISE might achieve what no Earth-based telescope can, detecting fine structural features of the nucleus itself. And then there's MAVEN, equipped with sensors to study Mars's upper atmosphere. By redirecting toward Atlas, MAVEN may be able to track its outgassing dynamics, especially the streams of carbon dioxide that dominate its unusual chemistry. Of course, none of this will be easy. These spacecraft were built to study a nearby planet, not a fast-moving comet speeding across the background stars at interstellar velocities. Their pointing systems will need real-time adaptation to lock onto something so distant, small, and faint. Even at closest approach, Atlas will rank around magnitude 12 to 14, a dim target pushing the limits of the orbiter's sensors. Colin Wilson of ESA has emphasized that while these observations are possible, the actual science return depends not only on instrument sensitivity, but also on timing, geometry, and even Martian weather conditions, the clarity of its thin but dusty atmosphere. Yet, the vantage point from Mars offers something Earth can't: different solar phase angles. The alignment of Sun, comet, and observer can expose coma structures and tail geometries invisible from Earth's perspective. Mars spacecraft might also detect Atlas interacting with the solar wind, the jet stream of charged particles constantly blowing off the Sun. Magnetic and plasma instruments carried by Mars orbiters could record how the comet reacts, opening a window into its interior makeup and electrical properties. Pulling this off will require unprecedented coordination. Mars Express was designed for geology. The Trace Gas Orbiter is fine-tuned for atmospheric trace chemistry. Yet now, both must step outside their original missions to become ad hoc comet observatories. Mission planners must carefully juggle schedules, communication windows, and bandwidth. Every observation of Atlas will have to compete with the spacecraft's primary tasks, and every bit of data must fight for transmission time across limited radio channels between Mars and Earth. If successful, though, the payoff could be game-changing. High-resolution imaging might once and for all pin down the size and shape of Atlas's nucleus, a debate still unsettled after months of Earth-based tracking. Spectroscopy from orbit could reveal molecular fingerprints never before measured, providing direct evidence of conditions in another star system's nursery. Plasma data might even tell us how alien dust and gas interact with the Sun's wind compared to comets we know from home. Mars orbiters are humanity's accidental lifeline. While Earth goes blind in October's glare, robots circling a neighboring world may give us answers we'd otherwise never see, answers that could change our understanding of interstellar objects forever. The Mars flyby might hold the answers to some of Atlas's most perplexing mysteries. From Earth, the comet's anti-tail, its baffling sunward plume, has defied explanation. But from Mars's unique vantage point, different phase angles could reveal whether this strange structure is truly material being launched toward the Sun, or if it's simply an optical trick of perspective. Still, managing expectations is important. These spacecraft weren't designed for comet hunting at interstellar speeds. Even under ideal conditions, the best we can hope for is a small set of images and spectra snapshots rather than the full movie astronomers wish they could capture. Much depends on forces beyond anyone's control. If Atlas brightens again before its October 3rd pass, it could momentarily blaze bright enough for orbiter sensors to lock onto it. But if it dims instead, the comet may slip from Mars's reach entirely, leaving those robotic eyes grasping at darkness. That's the razor edge of this opportunity. One chance, uncertain outcomes. Still, this flyby represents humanity's only lifeline during the critical weeks when Earth itself is blinded. With ground-based telescopes silenced by the Sun, the orbiters around Mars become our only hope of watching Atlas through its most volatile phase. Whether the data proves revolutionary or disappointing, the event marks something bigger, a turning point where humanity coordinates not just across borders on Earth, but across multiple worlds to study visitors from the stars. Even as Atlas speeds past us at interstellar velocities, the fact that machines circling Mars might provide the key insights shows how far we've come in our ability to chase cosmic mysteries. And then comes the part few astronomers want to acknowledge, Part 9: Superior Conjunction and Disappearance. The laws of celestial mechanics are mercilessly precise, and they don't bend for human curiosity. As October unfolds, Atlas inches ever closer to the Sun's apparent position in our sky. It's not the comet itself that fades, but our ability to see it. Superior conjunction, the moment when Atlas appears too close to the Sun to distinguish, will swallow it whole, turning one of the greatest astronomical events of our time into an invisible show. The sequence plays out with mathematical inevitability. In early October, Atlas drifts below the 30-degree elongation threshold, the point when sunlight scattering makes it nearly unobservable from the ground. Professional observatories, armed with powerful optics, hold out a little longer than amateurs, but by mid-October, elongation dips below 20 degrees. At that moment, even the best instruments on Earth give up. Atlas doesn't vanish instantly. It slowly drowns in the sun's blaze, fading out day by day until it's simply gone. And the cruel irony, this blackout overlaps perfectly with the comet's most important stage. Models forecast that peak outgassing, maximum tail growth, even potential nucleus breakups will occur near perihelion, late October. Exactly then, Earth-based telescopes will be helpless. It's as though the universe pulled a cosmic curtain right when the drama reaches its climax. Of course, there's no real conspiracy. The reason lies in the simplest geometry of all. Earth and the comet both orbit the same star. As Atlas approaches the Sun, its apparent position in our sky inevitably slides closer and closer to the overwhelming glare. Once lost in that render, no optical system can separate it from the solar background. No telescope, no adaptive optics, not even coronagraph systems designed to blot out the Sun for specialized solar missions. Atlas simply becomes invisible to us. In theory, solar observatories like SOHO, which carry coronagraphs to watch the Sun, can track comets during conjunction, but only if they skim extremely close to the solar disk. Atlas's trajectory won't bring it into SOHO's capture zone. That means even our specialized solar satellites will be blind during this critical window. This isn't just an inconvenient gap, it's a catastrophic hole in the record. Modern astronomy thrives on continuity, following objects across their full range of activity. Comet science, in particular, relies on this long view since eruptions, breakups, and fading phases all need context. The conjunction robs us of that continuity, cutting out the comet's most active, important weeks from direct observation. Yes, spacecraft positioned around the solar system can still play a role, and Mars orbiters are uniquely placed for this one chance. But their instruments weren't built for this type of study, and no matter how much they capture, the data will always pale next to what Earth's biggest observatories could have recorded if nature had allowed it. Atlas is approaching its trial by fire behind a blinding curtain of light. The moment of maximum revelation will unfold, but here on Earth we'll be left only guessing what secrets it spills as it brushes past the Sun. The Mars orbiters may offer us humanity's best look during October, but even their contributions will be snapshots rather than the continuous, day-by-day monitoring that astronomers crave. Brief glimpses, not the full story. Other spacecraft across the solar system could in theory step in, but their limitations are just as daunting. ESA's Bepi-Colombo mission, currently en route to Mercury, might catch a few lucky angles on Atlas, but its instruments were designed for planetary geology and magnetism, not delicate comet spectroscopy, and its orbit may not line up at the right times. NASA's Parker Solar Probe, a spacecraft plunging through the inner solar system to study the Sun itself, will fly through regions where Atlas's tail could extend. But while the probe is close enough to detect solar wind interactions, its instruments weren't built to monitor comets systematically. At best, it could stumble into Atlas's debris, an accident of geometry rather than a designed observation. The observational blackout also strikes a brutal blow to comet modeling. Theoretical predictions require constant feeding of new data, the very calibration points astronomers are about to lose. Without continuous brightness and spectroscopic readings, simulations can only guess how Atlas will behave in peak conditions. That guesswork will leave gaps no amount of computer power can fill. By the time Earth-based telescopes regain visual contact in late November or December, Atlas could be dramatically different. Perhaps it will emerge brighter than ever, its tail stretched wide and spectacular, glowing even in mid-sized amateur telescopes. Or maybe it will stumble dim and depleted, its volatile reserves burned away, and in the most dramatic possibility of all, Atlas might not survive intact at all. Fragmentation is not a rare fate for comets nearing their closest pass to the Sun. The immense forces at perihelion, heat, tidal stress, and rapid expansion from within can shatter weakly bound nuclei into multiple pieces. If Atlas breaks apart during its hidden passage, astronomers may return to a sky peppered with fragments instead of a single comet. Tracking and identifying those pieces will be a challenge, requiring global coordination to reacquire the comet after its disappearance. It won't reappear in the same place or the same form, and after weeks of invisibility, nobody can be sure exactly where to point their instruments to find it again. This gap isn't just frustrating for scientists, it also dulls public engagement. Media thrives on constant updates, images, and breakthrough discoveries, but during conjunction, Atlas will simply vanish from news coverage. The absence of new observations may mean that public attention fades right at the moment. The comet is undergoing its most profound transformations, and with it, educational opportunities are lost. Imagine the one interstellar visitor glowing ghostly green, possibly sprouting tails or fragmenting before our eyes, happening unseen. Teachers, students, and skywatchers worldwide will miss what could have been the comet's most dramatic teaching moment. It's a humbling reminder of astronomy's ultimate limitation. No matter how advanced our instruments become, we are still tied to a planet that orbits the same star we're trying to observe near. Even Hubble and JWST, marvels of modern engineering, cannot bend the geometry of our position. Once Atlas slips too close to the Sun in our sky, observation becomes impossible. And so, astronomers prepare for silence. Models will take over for data. Predictions will fill in the gaps. But what actually happens to Atlas in the weeks we cannot see, that may remain a permanent mystery, an unfillable blank in humanity's attempt to understand this messenger from beyond. Then comes the climax, the date that's been looming all along. Part 10, Perihelion Expectations. Hidden deep within the Sun's glare, completely invisible to Earthbound telescopes, Atlas will reach perihelion between October 29th and 30th, 2025. There, 1.36 to 1.4 astronomical units from the Sun, it faces the most brutal solar radiation of its existence. After millions of years wandering frozen between the stars, Atlas will meet its trial by fire. The numbers are staggering. Today, Atlas races at tens of kilometers each second. Near perihelion, it will crest to an astonishing 68 kilometers per second, over 152,000 miles per hour. Earth itself only crawls along its orbit at about 30 kilometers per second. Atlas will be moving more than twice that speed. carrying unimaginable kinetic energy built up through its journey across the galaxy. This is raw interstellar power, directed now toward the Sun. At these extremes, physics predicts chaos. As the nucleus absorbs the Sun's full heat, every volatile compound inside, water ice, carbon dioxide, carbon monoxide, and more exotic frozen gases, will ignite in a frenzy of sublimation, exploding outward. The coma may balloon to sizes dwarfing even the already unbelievable 348,000 kilometers seen in September. Jets of gas could erupt like fountains from hidden pockets in its crust, blasting dust and rock into space, flaring like geysers thousands of kilometers long. And then, the ultimate unknown, will Atlas's bizarre anti-tail, the sunward plume that defied science all summer, intensify, glowing brighter in the sun's fury. Will new tails emerge as different frozen elements activate for the first time in billions of years? Or will the comet buckle under its own instability, splitting into shards no model predicted? At perihelion, hidden from our direct sight, the fate of the third known interstellar visitor will be decided. Models suggest that Atlas's carbon dioxide-heavy composition could produce a spectacle near perihelion, unlike anything seen in typical water-dominated comets of our solar system. Solos sublimates more easily than water ice under solar heat, meaning Atlas might erupt with activity at levels multiple times higher than we've ever observed in familiar comets. Instead of slow, predictable changes, its brightness, tail length, and coma size could shift over mere hours, evolving rapidly in ways that break every rule astronomers are used to applying. But hanging over every prediction is an ominous possibility: fragmentation. Comets are among the most delicate bodies in the cosmos, loosely bound clumps of ices and dust, barely held together by gravity and fragile chemical bonding. The violent stresses of intense solar heating, compounded by jets of gas bursting explosively outward, can rip these fragile worlds into pieces. Often it happens suddenly. A comet can seem stable one day and split into shards the next, as cracks spread and internal pressure bursts through weak points. If Atlas suffers such a fate during perihelion, Earth-based observers will reawaken in November, not to one object, but to a shattered swarm of fragments streaking away into deep space. History provides sobering precedent. In 1994, Comet Shoemaker-Levy 9 fractured under Jupiter's immense tidal pull before slamming into the planet in spectacular fashion. More recently, Comet Eisen in 2013 disintegrated during its perilous plunge near the Sun, leaving behind only a dispersing trail of dust. Atlas could join that list, or it could surprise us all by holding together. The outcome depends on its inner makeup, things like its porosity, strength of bonding, and rotation rate. All great unknowns for an interstellar body, and unlike slow-moving comets that linger near the Sun's furnace, Atlas is blazing across perihelion on a hyperbolic path. Its sheer velocity may shorten the heating time enough to reduce its risk of destruction. If Atlas survives, the weeks after perihelion will be equally fascinating. The coma could erupt to even vaster sizes, spreading particles and gases across volumes dwarfing those observed in September. Gases buried deep for billions of years could suddenly vent into space, producing brand new chemical signals detectable in spectra. Its glow could take on additional colors, reds, blues, or golds, if unfamiliar organic materials break apart into fragments that fluoresce under ultraviolet radiation. The haunting green glow we've already seen might transform into a spectrum of exotic hues, the comet's chemistry revealed in a rainbow of photons. The mysterious anti-tail, its sunward plume, may also change dramatically. Dust jets erupting from newly exposed layers could generate multiple tails pointing in different directions, shaped by particle size and solar pressure. The geometry of these structures could finally unlock details about Atlas's nucleus, its spin, its composition, even patterns of buried volatiles erupting like cosmic geysers. Dust analysis is particularly crucial. Big grains streaming into the coma can hint at a loose, porous nucleus with vast empty voids, while clouds of fine dust would suggest a denser composition or unusual chemistry. The size and spread of debris will act almost like a fingerprint for Atlas's interior, the closest thing to taking a core sample of a star system light years away. Then there's the drama of its electromagnetic environment. As solar wind rushes past, those streams of charged particles will slam into Atlas's ionized gases, shaping plasma tails stretching millions of kilometers. Electric and magnetic interactions may accelerate particles to extreme speeds, create ghostly glows visible from afar, and warp the coma in ways no purely physical model could explain. If spacecraft capture these effects, they may decode Atlas's hidden electrical and magnetic properties, ingredients that shape how comets interact with stars across the galaxy. Temperature readings, if orbiters or distant probes can capture them, may prove game-changing. Each volatile element within Atlas vaporizes at its own distinct threshold. Tracking which compounds sublimate at which temperatures essentially creates a thermometer for the nucleus, revealing how deeply the sun's warmth penetrates and what layers lie beneath its surface. The aftermath of perihelion will hinge on how rich Atlas is in volatile reserves, and how efficiently that material can escape. A nucleus rich in ices may keep erupting for weeks or months after, fueling long-lived activity, but a more limited supply could sputter out quickly, leaving Atlas to dim into obscurity almost as soon as it returns to Earth's skies. Even the sun's immense gravity might slightly alter the comet's path. While its hyperbolic trajectory ensures it won't be captured or return, tiny gravitational tugs during perihelion might shift its angle or tweak its timing as it sails outward. Those subtle nudges could change its future alignments, particularly with the outer planets, setting up its planned encounter with Jupiter in 2026. Ultimately, perihelion is the climax. Billions of years of frozen isolation meet the unimaginable fury of our star. Whether Atlas blazes brighter, bursts apart, or quietly transforms beneath its coma, it will never again be the object that entered our skies in quiet anonymity. Whatever emerges will be something new, reshaped, reborn, or reduced to dust. And the haunting question remains, when we finally see Atlas again after the glare of the sun subsides, will it still be the same alien comet that shocked us in September, or will we be staring at the wreckage of something that didn't survive its fiery encounter with SO? This brings us to part 11, comparisons with past interstellar visitors. To understand the scale of Atlas's anomalies, we must look at the only two interstellar travelers to precede it. In 2017, astronomers spotted the first One-Eye Fomalhaut, discovered by Pan-STARRS in Hawaii. It confounded expectations right away. No coma, no tail. Instead, a bizarre elongated shape estimated at 400 meters long and just 40 meters wide. A cosmic cigar, unlike anything in our solar system. Stranger still, as it left the sun, it accelerated in ways no gravity model could explain. Was it unseen outgassing, radiation pressure pushing on an oddly thin body, or something stranger still? Theories multiplied, but no definitive answers came. Oumuamua challenged our definitions from the moment it appeared. 2 years later came 2I/Borisov, discovered in Crimea by amateur astronomer Gennady Borisov. At first glance, it looked far more ordinary. A classic comet with a coma and tails, yet hidden within its chemistry were alien fingerprints. Its levels of carbon monoxide were far higher than typical in our comets, suggesting it formed in far colder and chemically distinct conditions than our solar cloud provided. Even what looked normal on the surface turned out to be distinctly foreign underneath. Now enters 3I/Atlas, and compared to its predecessors, it's rewriting rules at hyperspeed. Its CO-Fols-rich coma is the sharpest compositional deviation from solar system comets yet recorded. Its sunward-pointing anti-tail defies textbook physics entirely. Its runaway brightening trend stands out as unprecedented, not seen in either Oumuamua or Borisov's passages, where the first was mysterious and cometless, and the second deceptively ordinary. Atlas is spectacular, volatile, and unstable. Even its size falls into an uncertain category. Oumuamua was slender and asteroid-like. Borisov's nucleus, at about 1 kilometer, fell into the expected range. Atlas's nucleus remains poorly constrained, between 0.3 and 5.6 kilometers, its precise measurement complicated by its immense coma. That uncertainty, too, reflects its mystery. It eludes clean categorization. Taken together, these three interstellar visitors are a reminder that the galaxy does not produce one-size-fits-all small bodies. Instead, each system forges its own creations in ice, rock, dust, and gas. And when those creations are flung into interstellar space and eventually wander into ours, They carry with them evidence of alien nurseries, snapshots of environments unimaginably distant in both space and time. What sets Atlas apart is that it isn't just unusual compared to comets from our own solar system, it's even stranger than the interstellar visitors that came before it. The tools available now let astronomers probe its secrets at a level unimaginable just a decade ago. The Dumour, discovered in 2017, gave scientists precious little to work with. It released no visible gas, offered no coma, and its time in view was brief. All researchers could measure were its reflective properties and anomalous motion. Borisov, discovered in 2019, was more cooperative, displaying a familiar coma and tail, which let spectroscopes detect water vapor, carbon monoxide, and other molecules. Atlas, however, benefits from the full arsenal of today's advanced instruments. The James Webb Space Telescope's infrared eyes, Hubble's sharp imaging power, and next-generation ground observatories now provide chemically detailed snapshots of an interstellar visitor at a level far beyond what earlier objects revealed. The orbital paths of these visitors also tell stories of their deep galactic origins. The Dumour arrived from the direction of Vega, though its travel time far exceeded the age of that star, showing that its trajectory was shaped by countless interactions across the galaxy. Its recorded exit speed, 26 kilometers per second beyond solar gravity, already exceeded anything a solar system comet would achieve on its own. The Borisov entered faster still, at about 32 kilometers per s, hinting at either origins in a high-energy birth system or accelerations gathered through stellar flybys. Atlas now pushes that bar to its highest yet, 39 kilometers per s. This colossal velocity almost certainly means it was ejected violently from its home, or was whipped to new speeds by multiple encounters on its way here. The speed itself has consequences for perihelion, shortening the exposure time under maximum heating and potentially influencing whether the nucleus fractures or endures. The discovery timelines of each visitor also reveal hints about how often they pass through. Dumour was detected in 2017, followed by Borisov in 2019, then 6 years later came Atlas in 2025. That cadence suggests that interstellar travelers may pass through more regularly than we once believed, but spotting them remains difficult. They are faint, fast, and their windows of visibility are short. Each detection feels monumental not because they're rare, but because catching them demands perfect alignment of timing, technology, and luck. Together, these three interstellar messengers highlight staggering diversity. The Dumour looked more like an alien shard of rock than a comet. Borisov seemed textbook normal until spectroscopy revealed chemistry far outside anything local, and Atlas has managed to defy nearly every model at once. Its Corthert-rich atmosphere, its gigantic coma, its bizarre anti-tail, its explosive brightening trend, each feature adding to the growing realization that the Milky Way's comets come in forms our imagination hasn't even caught up to yet. And even now, as Atlas disappears behind the sun, scientists admit that more surprises are almost guaranteed to emerge after conjunction. If history with the Dumour and Borisov is any guide, Atlas will almost certainly return to view in late November, bearing new anomalies, ready once again to confound and expand human understanding. This brings us to part 12, the unknowns and the debates that rage behind observatories and conference halls. Right now, studying Atlas feels like trying to solve a cosmic detective story with half of the evidence hidden behind a locked door. The biggest question marks remain centered around its physical size, its makeup, and the forces driving its bizarre structures. One of the most frustrating mysteries is the nucleus itself. Hubble pinned its possible diameter somewhere between 0.3 and 5.6 kilometers, a huge range that only highlights the problem. The nucleus is drowned in its immense coma, making separation nearly impossible, and size matters. It determines the comet's total mass, its density, how much surface material can gas off, and even how long it can withstand the strain of perihelion heating. But even with the sharpest instruments, astronomers can't agree. Infrared thermal models paint a picture of a small but icy, highly reflective core. Visible light studies suggest something darker, larger, and more heat-absorbing. The two views cannot both be right, suggesting either measurement error, surface differences, or something fundamentally new about how Atlas interacts with solar energy. The chemical signals add another headache. James Webb's readings clearly showed Atlas dominated by carbon dioxide, far above its water vapor content. That breaks with almost every solar system comet, where water usually takes the lead. And yet, in September, Atlas lit up green, a signature usually caused by diatomic carbon, ClO. But a CO-Therodevi comet shouldn't easily produce that much free carbon. Is Webb missing something? Are there hidden reservoirs of organic compounds breaking down? Or are reaction pathways here so alien that they're unlike anything we've modeled before? Ground-based spectrographs add more complexity, detecting cyanide, organic molecules, and other exotic species that don't fit neatly with Webb's assessments. This growing list suggests that Atlas's chemistry is a layered mix of simplicity and sophistication, with hidden compounds erupting under solar duress. Then there's the infamous anti-tail, the plume pointing toward the sun, when physics demands it point away. Theories abound. One proposes Atlas ejects unusually large dust grains. These particles are so heavy that they resist being blown away by sunlight, and thanks to their ejection speeds, they settle into a geometry that looks like a sunward plume. Others argue the explanation may lie in electromagnetic fields, solar interactions with charged dust that can bend trajectories in strange directions. Rotation has also been floated as a culprit. If Atlas spins oddly or slowly, it might create hot and cold sides that funnel activity into focused jets, regardless of solar pressure. But here's the catch. We don't even know Atlas's rotation period. Months of analysis have found no clear rhythmic change in brightness that could indicate how fast it spins. That absence might mean Atlas rotates so slowly the pattern is buried in noise, or that it's shaped so smoothly brightness doesn't fluctuate, or perhaps that its rotation itself is chaotic. Without knowing its spin, predicting how it outgasses or how close it is to breaking apart becomes nearly impossible. Even its brightness surge in September, the phenomenon that first caught global attention, remains debated. Multiple networks confirm Atlas rose far faster than predicted, but they disagree on scale. Some claim it leapt several magnitude levels brighter. Others see a smaller though still unusual deviation. The truth may sit between them, or it may reveal another layer of how measurement difficulties cloud an already complicated story. Atlas, in short, is a riddle that keeps getting harder the closer we look. Every answer spawns new questions, and every observation contradicts models that seemed solid weeks earlier. 3I Atlas sits right at the edge of what even our best telescopes can consistently detect. Measuring its brightness is a challenge. Different astronomers use different comparison stars, filters, and reduction techniques, all of which introduce slight inconsistencies. More importantly, there's no baseline to compare against. Periodic comets give us years of history to guide predictions, but Atlas is a one-time event. There's no previous encounter with the sun to provide context. That means scientists are forced to lean on models built for local comets, models that may not translate well to something that was born in another corner of the galaxy. Tracing its birthplace only adds more uncertainty. Using its current speed and direction, astronomers have tried to roll its trajectory backwards through the Milky Way to pinpoint its origin. They suspect it came from the thin disk of the galaxy, the dense star-rich plain where most stars and planets are born. But the farther back you extrapolate, the fuzzier the data becomes. Small uncertainties in its speed and position snowball, spreading its potential origins across vast swaths of space. Did it form in a young, still developing star system carrying the pristine chemistry of a solar nursery? Or did it condense billions of years ago around an ancient evolved star under conditions nothing like our neighborhood? Its carbon dioxide-dominated chemistry might be the clue, but without more context, its true birthplace remains guesswork. Even Atlas's structure is debated. Its massive coma and strange sunward plume could suggest a nucleus rich in volatiles, constantly venting gas, or it could mean the entire nucleus is unstable, a rubble pile barely held together, primed for breakup. Others argue it may actually be monolithic, solid but laced with exotic surface materials that release gas in extraordinary ways. The distinction means everything. A rubble pile could shatter apart near perihelion. A solid nucleus might endure but display unconventional vents and jets. Which it is, nobody can yet say. Another unresolved puzzle is the switch-on moment in early September, when Atlas suddenly brightened as it crossed the 2 AU threshold. Did this mark the activation point of a volatile compound with a precise sublimation temperature? Or did sunlight uncover long-buried deposits of exotic ices hiding just beneath the surface? In our solar system, water starts gassing out around 3 AU while carbon dioxide remains active at far greater distances. Atlas may contain a layered cocktail of ices with activation triggers offset from anything we've studied before. Different compounds lighting off at different thresholds could explain its erratic bursts of brightness and hint at exotic materials never seen in local comets. The conjunction gap will make it nearly impossible to sort competing models until later in the year. The most critical tests, how Atlas handles maximum solar heating, whether it fractures, whether its antitail persists, will play out while Earth lies blinded by the sun. When it emerges in late November, we may be staring at a completely different object. Validating or refuting, the current models will be far harder, with so many pieces of evidence missing. And yet, this is the nature of studying interstellar objects, rare, fleeting, and often operating outside any framework built from local examples. Atlas has forced researchers to confront the possibility that the rules we apply to comets may not be universal. Some behaviors may be governed by physics that only reveals itself under extreme alien conditions. Every measurement is uncertain. Every model is provisional. Every theory is conditional on the idea that we may still be missing something fundamental. This brings us to part 13, natural explanations. Before scientists stray into speculation, they must first exhaust every explanation that lives within the boundaries of known physics, even if those processes are pushed to extremes we've never witnessed. The carbon dioxide dominance, for instance, might be perfectly natural. Its presence suggests Atlas formed in a region of its birth system where the Ceothydes snow line was the dominant frontier. The snow line marks the distance from a star where temperatures drop enough for gas molecules to freeze into ices. In our solar system, the Ceothide line lies far beyond the regions where most comets originate, which is why our comets are largely water-rich. But not every star system is like ours. Cooler stars might push the Ceothide snow line inward, making Ceothide-rich comets common. Alternatively, its home star might simply have had a chemical balance tilted toward carbon, ensuring carbon dioxide froze abundantly where water would otherwise dominate. This alone could explain Atlas's unusual composition, and also its volatility. CO sublimates more easily than A2O, meaning it releases gas far more energetically under the same solar heat. That enhanced volatility could naturally explain September's runaway brightening and the outsized coma revealed by Spherex. Yet composition alone doesn't explain everything, most notably the sunward-pointing anti-tail. This is where plasma physics enters the scene. When ultraviolet light from the sun strikes Atlas's coma, it ionizes gas molecules, turning them into plasma, a swarm of charged particles influenced not just by gravity, but by magnetic and electric fields carried in the solar wind. These charged gases interact with cometary dust in complex ways, creating filaments and streams that can self-organize into patterns we don't typically see. In extreme environments, plasma dust coupling could actually push material sunward while lighter components stream outward, producing the anti-tail we see. Atlas's unusually dense coma, created by enhanced Ceothide activity, may provide exactly the conditions for this effect to become pronounced. Rotation could also be a factor. If Atlas rotates very slowly, one side may bake for far longer than comets in our solar system normally do. That prolonged heating could generate concentrated jets blasting sunward, overpowering the usual physics that shapes tails. A slow spin might also explain why astronomers have struggled to detect a clear rotation period in brightness data. If the nucleus doesn't spin noticeably within the observation window, periodic signals would vanish into background noise. And then there's the green glow. This too may be explicable through timing and thresholds in gas release. As Atlas crossed the 2 AU mark, solar radiation may have broken down CO hive into carbon monoxide and free oxygen, then further photodissociated CO into fragments that recombined as diatomic carbon, CaE. This fragile molecule fluoresces under ultraviolet light, producing the bright green halo that suddenly appeared in September. In other words, the greenness may not come from reserves of carbon-bearing gases leaking out, but from chain reactions triggered in the coma itself as radiation tore molecules apart and reassembled them into new ones. Alternative explanations involve trace organics buried within the nucleus released in just the right conditions to energize previously invisible emissions. These complex carbon compounds would break down under solar exposure, releasing fragments that glow in unanticipated colors. One thing is clear: even if Atlas's behavior pushes our ideas to their limits, every aspect of it still fits barely within science's reach. No need for exotic theories yet. Just extreme physics, extreme chemistry, and extreme conditions now finally on display after billions of years in the dark. One possibility is that Atlas's strangeness can still be explained by natural chemistry rather than anything truly alien. Organic molecules like polycyclic aromatic hydrocarbons, amino acids, or other complex carbon-based compounds may be embedded in its surface. As the sun bombards the comet with radiation, those compounds could fragment into glowing carbon byproducts. That chain of breakdowns may generate the emerald green light we now see spreading across the coma. Variations across the comet's surface could provide another clue. Rather than being a single uniform ball of ice and rock, Atlas may be a patchwork world with regions rich in CO2, others full of water ice, and still others laced with complex organics. As different regions of the comet rotate into sunlight for the first time, we may simply be watching entirely different volatile inventories ignite in sequence. Porosity adds yet another angle. Imagine the comet as a sponge of ice and dust, highly porous, full of voids, and far weaker than most solar system comets. In such a structure, heat from the sun can penetrate much deeper, unlocking reserves of gas buried far within. That could explain the comet's extra-wide coma and sudden volatile brightening events. Atlas may be venting from its depths, not just its surface. On top of that, centuries of cosmic ray bombardment, constant dust grain impacts, and thermal cycling as it drifted through interstellar space may have altered its structure in ways no solar system object has experienced. In the end, the most likely explanation is not one single cause, but a cascade of overlapping ones. Pseudo-chemistry driving hyperactive outgassing, plasma interactions shaping the bizarre anti-tail, slow or unusual rotation concentrating localized activity, and complex carbon chemistry triggering color changes. That would make Atlas an extremely strange comet, yes, but one still consistent with the universe we know. Still, whenever science hits its limits, speculation escapes through the cracks, which brings us to part 14, exotic and fringe theories. Whenever a cosmic visitor behaves in ways no model neatly explains, the human imagination leaps into overdrive. Oumuamua, the first interstellar object discovered in 2017, immediately sparked debates about artificial origins, so perhaps it's inevitable that Atlas's strange behavior has invited some of the same. The first speculative idea is the alien beacon hypothesis. In this scenario, Atlas is a dormant probe, an ancient machine wandering between the stars, built to awaken under the energy of a new sun. The sudden surge in brightness, the anti-tail, even the swollen coma would then represent activation systems kicking in, as though the comet were switching itself on after eons of silent travel. But while evocative, the evidence doesn't fit this narrative. Every spectroscopic reading so far shows conventional chemistry, carbon dioxide, water vapor, organic molecules, exactly what you'd expect in natural comet outgassing. No artificial alloys, no unexplained energy signatures, no isotopic oddities that would betray technology. For now, the beacon theory remains in the realm of imagination. Another far stranger suggestion is the living plasma hypothesis. In the lab, dusty plasmas, mixtures of charged gases and fine particles have shown surprising abilities to self-organize, with patterns that can mimic biological behavior. Some researchers have mused that such complex plasmas could, in theory, act almost like proto-life forms. Viewed through that lens, Atlas's erratic jets, strange forward plume, and pulsing brightening events might be interpreted as the behavior of a plasma-based organism responding to solar input. Could interstellar space harbor forms of organization that mimic life through physics, not biology? It's a dramatic thought. But here too, the evidence runs thin. Scaling dusty plasma effects to something comet-sized stretches plausibility, and no electromagnetic signatures suggesting living plasma behavior have been detected from Atlas. Then there's the most cinematic of all, the scout ship narrative. Perhaps Atlas isn't just an ancient artifact, but an active probe scanning the solar system, pre-programmed to wake at perihelion, survey nearby worlds, and transmit data back across the cosmos. In that scenario, its green glow might be sensors activating, while brightness surges reflect bursts of energy-intensive data transmission. Romantic as that notion is, once again, reality is less forgiving. The chemical and thermal signatures of Atlas look exactly like what you'd expect from an exotic but natural comet, not a programmed surveyor. No directed signals, no anomalies outside physics, just cometary chemistry acting in overdrive. Others push even further out into the realm of exotic matter. Could Atlas contain materials unknown to modern physics? Theories involving interactions with dark matter, or phase transitions driven by principles we haven't yet discovered, have been invoked as possible explanations for its unorthodox behavior. In this view, Atlas wouldn't be a machine but a laboratory of physics beyond the standard model, an interstellar fragment dense with phenomena our equations can't yet accommodate. While tantalizing, this remains speculation stacked atop speculation. Finally, the most extreme conjecture, temporal anomalies. The idea that Atlas is not just from another place but another time, that it could somehow be a message or artifact sent backwards across centuries, carrying information from our far future into our present through mechanisms we can barely imagine. Science doesn't support this, of course, but as with all cosmic mysteries, the strangest possibilities inevitably stir the imagination. In the end, all of these fringe theories remind us not that Atlas is artificial, but that its behavior is so unusual it invites comparisons to science fiction. For now, every shred of evidence still points to a natural object, a profoundly strange, profoundly alien comet by solar system standards, but still governed by physics. And perhaps that's the most breathtaking fact of all. Even without rewriting the laws of nature, Atlas is forcing us to expand them, showing us corners of physics and chemistry we've never witnessed until this very moment. Some of the most imaginative theories about 3I Atlas suggest scenarios straight out of science fiction. A probe from the future, a messenger traveling backward through time, or even a signal-bearing artifact designed for our age. But the reality is harsher. Physics as we know it would not allow such temporal manipulations without tearing apart causality and thermodynamics themselves. And so far, nothing Atlas has shown us violates energy conservation or betrays the fingerprints of time-bending technology. This isn't the first time astronomy has flirted with the extraordinary. Pulsars were once nicknamed LGM, Little Green Men, because their precise radio pulses seemed artificial. They turned out to be spinning neutron stars. Fast radio bursts, too, were briefly thought to be alien signals before revealing themselves as natural high-energy phenomena. History is clear. Nature can mimic the fantastic, but always with processes rooted in physics. Atlas almost certainly belongs in the same category, an extreme natural object, not a cosmic machine. Yet the mere fact that its behavior invites such speculation is a sign of how extraordinary it truly is. Any comet capable of sparking debates about alien probes, plasma, life, or exotic matter has already broken the boundaries of the ordinary. Which brings us at last to part 15, the countdown and the implications. The clock is ticking. Atlas is racing toward a series of milestones that will decide not just what we learn about this one visitor, but what it teaches about the untold population of interstellar objects quietly drifting through the galaxy. Each date ahead is a test of our telescopes, of our spacecraft, and of our ability to decode messages hidden in ice and dust, forged around another star. The first critical checkpoint comes October 3rd. On this day, Atlas sweeps closest to Mars, just 30 million kilometers away, for the armada of spacecraft orbiting the red planet. This is a chance unlike anything before, the chance to turn instruments never meant for comets toward an object traveling at interstellar speeds. Mars orbiters will strain their cameras, spectrometers, and detectors, hoping that Atlas stays bright enough for meaningful data. But the success of that handoff depends on fate. If Atlas dims, the observations may be little more than static. If it remains blazing, Those robotic eyes may capture secrets Earth will never see again. Then October 29th, 30th perihelion, the hidden climax. At these distances, 1.36 AU from the Sun, Atlas will endure solar intensities unlike anything it has faced in its million-year journey across the galaxy. Volatile compounds buried deep in its core will ignite in a frenzy, producing eruptions strong enough to change the very shape and chemistry of the comet. This is the moment astronomers have waited for, the trial by fire. But it will occur almost exactly as Atlas disappears into the Sun's glare. The cruelest irony of all, the grand transformation, the peak of energy and violence that defines the comet's story, will unfold behind the curtain, invisible to Earth. For 4 to 5 agonizing weeks, from early October through early November, 3I Atlas will effectively vanish. Fragmentations, surges, chemical fireworks, none of it will be seen. Instead, models will take over where observation fails, leaving us to speculate about what's happening at the very center of the drama. And then, in early December, the curtain will finally lift. Through the haze of twilight, telescopes will reacquire Atlas, and the question will be answered: did it survive, did it split, or did it dim into irrelevance? The comet we find in December might look nothing like the one we last saw in September. The post-perihelion phase will open new windows. Jupiter awaits in March 2026, when Atlas passes within range of possible spacecraft detections by Juno or the upcoming Europa Clipper. Though not as close as the Mars encounter, these opportunities may extend its story further as it begins its long departure from our system. But the implications stretch beyond Atlas itself. Every chemical ratio detected, every brightness anomaly recorded, every plasma effect measured, each one assigns a new data point to the map of interstellar diversity. Atlas's K-wall dominance suggests that planetary systems across the galaxy forge comets under wildly varying conditions. Its anti-tail forces scientists to rethink how gas, dust, and electromagnetic fields interact under stellar winds, and its runaway brightening tells us our models of volatile release are incomplete. This one comet, just the third proven interstellar visitor, is already rewriting planetary science. Together with its predecessors, the Zhumou, and Borisov, Atlas acts as an ambassador of cosmic diversity. It whispers that other star systems don't produce familiar comets and asteroids, but strange hybrids governed by rules written in nurseries far different than our own. Every interstellar object we catch will expand the spectrum of what's possible. And Atlas has already proven one thing beyond doubt. The galaxy is far stranger, richer, and more inventive than the boundaries of our imagination. If Atlas does break apart during perihelion, that destruction could become its greatest gift to science. Each fragment would act like a natural core sample, pieces of an ancient body forged around another star, ripped open to expose material from its hidden layers. Spectroscopic analysis of scattered fragments could reveal compositional gradients we've never seen, offering direct access to the chemistry of alien planetary nurseries. It could be the closest humanity ever comes to holding samples from inside another star system, delivered by a cosmic accident. But expectations must be tempered. Atlas will never dazzle the unaided eye, the way great historic comets have. Peak brightness is likely to hover around magnitude 11 or 12, visible only through telescopes, invisible to casual skywatchers. This may limit the grand public spectacle, but scientifically its value cannot be overstated. Its lessons lie in chemistry, physics, and structure, not in spectacle. The challenge it presents today illuminates the need for tomorrow's technology. Missions like ESA's Comet Interceptor, set to launch in the late 2020s, are being designed to lie in wait near Earth's low dew point, ready to pounce on the next newly discovered comet, or perhaps another interstellar wanderer. But the truth is this: Atlas was discovered too late. By the time its nature was clear, there wasn't enough time to redirect a mission. The lesson is clear. Future detection systems must spot these messengers years in advance, not months. And those systems are coming. The Vera C. Rubin Observatory in Chile, with its legacy survey of space and time, promises to revolutionize the field. With unprecedented sky coverage and nightly imaging, Rubin could detect interstellar visitors far earlier, perhaps several each year. Instead of rare, lucky encounters, interstellar science will soon be systematic, a steady stream of messengers rather than chance arrivals, expanding our catalogue of alien chemistry and structure beyond anything imagined. Next-generation instruments will push this further. Giant ground telescopes like the 30-meter telescope and the European Extremely Large Telescope, combined with orbiting observatories that break free from Earth's atmosphere. Together they will give humanity the power to measure even faint, fast-moving objects with unheard-of precision. Data standards and global coordination sharpened during the Atlas campaign are already becoming templates, setting the stage for future rapid-response interstellar discoveries. And these efforts, though technical, touch the deepest questions we can ask. Astronomically, Atlas is direct evidence of conditions in other star systems frozen into a pristine time capsule and delivered to our doorstep. Astrobiologically, it raises profound possibilities. Interstellar objects may be vectors of organic chemistry, maybe even the raw ingredients of life, moving silently between suns, sowing the Milky Way with complexity. While no evidence suggests Atlas carries anything alive, its unusual chemistry proves that complex organics can endure star-to-star journeys, and that has implications for the cosmic spread of life. Even planetary defense benefits. Atlas is no threat to Earth, but its unpredictable volatility shows just how limited our current models are. If a future interstellar comet one day barrels toward us, confidence in forecasting its behavior could mean the difference between preparedness and disaster. Atlas is the warning shot that unpredictability itself is something we must learn to model. And then there's the narrative, the chance to inspire. Though faint in the night, Atlas still captures the imagination of students, amateur astronomers and educators who use it as a living example of science in real time. It reminds us that discovery isn't just about answers. It's about the chase, about confronting the unknown with curiosity sharpened into observation. Commercial industry is watching too. Companies exploring asteroid mining and resource extraction are learning from the tracking systems, spectroscopic tools, and analytical frameworks honed on Atlas. Every interstellar object we study not only expands cosmic science, it builds the engineering base for future exploration, perhaps even utilization of small bodies closer to home. And so, as October approaches, the stage is set. Atlas won't light up the sky like a mythical visitor, but it has already reshaped how we think, how we organize science, and how we prepare for messengers from beyond. It is a time capsule of alien chemistry, a testbed of physics under conditions we have never witnessed, and perhaps the strongest reminder yet that our galaxy manufactures diversity beyond imagination. In the weeks to come, 3i Atlas will either blaze into an eruption beyond all precedent, fracture into a cosmic spray of debris, or simply skim past the sun and fade, retreating forever into interstellar cold. Whatever path it takes, the comet has already fulfilled its role. It has forced humanity to confront the unknown, to innovate, and to imagine. And now all that remains is to watch, to see what message this emissary from another star will carry as it reveals its final secrets in the heart of our solar system. The countdown has begun.